Hey, everybody. Welcome to the very last lecture of computer graphics this quarter. We made it through Mardi Gras and a week of snow and cold here in Louisiana. So I guess we should be congratulated. But anyway, we've reached the last lecture. So today we're going to be finishing up ray tracing and getting you a little bit more familiar with assignment 5, which is the final assignment that will be due a week from today. As far as the calendar goes, Wednesday and Friday we have our final project presentations. If you check Moodle, you'll see that the evaluation sheets are now up for that. I think I have them locked until Wednesday at class time. Some of you are going on Wednesday and some of you are going on Friday. I'll do it the reverse of what I did last time. I think we went alpha last time, so this time we'll go reverse alpha order, just to be fair to everybody. Let's see, so we've got those on Wednesday and Friday, and then the following Monday, that's actually March 1st is actually the last day of class, but we're not going to have a lecture. Instead, I'm just going to spend the whole day doing code review sessions. So there won't be a lecture on Monday, March 1st. We'll just do code review sessions instead. Are there any questions before I get started with the lecture? Any questions at all? Okay. All right. Okay. So, one other little thing I did want to do. One second, I'm putting it in chat. Everyone who is here will send me an email with that subject line. I'd appreciate it. If you go ahead and do that, that would be great. There are 16 of you here today, so I will expect to see 16 of those emails in my inbox here in the next couple of minutes. So you need to do it like right now. Take a moment, send an email with that subject line. Obviously, your name is your name, and it's not YOURNAME. And I figured out what I'm going to do with it. I did a lot of mentions that we needed more people to attend lectures because unfortunately some people aren't getting the homework or aren't getting the programming assignments, and I really should mute this, it's annoying. I've mentioned that that some people are struggling with the programming assignments, and I think that that we would be getting better results if more people showed up. I've got 9 so far of the 15 of you who are here. But anyway, yeah, I've figured out what I'm going to do with them. If there is a class curve, which there may be, if you showed up these days that I sampled, then you'll participate in the class curve. And if you didn't show up on these days that I sampled, you won't participate in the class curve. So I think that that's how I've decided that I'll use these. So you know, I'm not penalizing people who chose to not show up, in that they'll get the grade they earned. But if you did show up and you're right on the border, and I have a class curve, then you might get bumped up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12. There are 16 people in the room, but I've gotten 12 emails so far. Maybe a couple of people don't want the points. Oh well, that's fine. Okay, now we're going to move on. Oh, and by the way, if I end up with more than 16 of these, all bets are off. In other words, don't be passing this around to people who aren't here, trying to be nice to them, because it'll cost everybody. Okay, I'm supposed to be sharing my screen here. Let's see. Okay. So we talked about ray tracing last time. The most important thing about it is the rays are traced backwards, going from the center of projection, where of course that's where your eyeball is, right? At least it's everything is rendered as if you're looking from the center of projection. So the rays shoot out of your eyeball, they go through the pixels of the screen, and they go into the environment, and maybe they hit things and maybe they don't. And if they hit things, maybe they bounce around, reflect and refract. And so we build up an image or a pixel from the interaction of the various rays. It can be extremely expensive, as we mentioned, because you can have things like, hold on, you know, a typical scene that you're going 4 levels deep that had both reflection and refraction, you could have up to 15 intersections, all to compute 1 pixel. And you do that over and over. Now, we did say that there are some ways of limiting the damage or the expense. That's, of course, the recursive calls. That's a pseudocode for the algorithm. If you get rid of the refracted rays, you turn what is an exponential computation into a linear computation. So you'd only do, in this case, 1, 2, 3, 4 intersections versus 15 intersections to go 4 levels deep. We also made the very obvious point that you can't do backface removal or anything like that because things can be reflective. You can see the back of something. You can see the back of one object in the front of another object. So backface removal is off the table. So where we ended up last time is we were talking about the computational details of intersections, reflections, and refractions. And so the first thing we did was looking at intersecting a ray with a sphere. So basically what we do is we get a equation for this light ray. And basically that equation, you can have the light ray as long as you have a vector like ijk for x, y, and z, that's where this points, and an anchor point, could be either the eyeball or the screen pixel, but you need, it can be any point along the ray, but you need both a direction and you need an anchor point for the ray, okay? And we're interested in spheres here. Well, a sphere is all points that are radius distance away from some center point. So you'll need to know the center point of the sphere, and we're using LMN for that because, of course, we're using X, Y, Z's for the points along this ray here. So the X, Y, Z of the center point of the circle or the sphere is LMN. The radius is R. And basically, what we do mathematically is we come up with a parametric equation for this line, right, defined by this vector and a point on it. And by parametric equation, I mean we'll have a parameter, we'll call it t, and t says, okay, from the starting point, if you're going in this direction, t is how far you go along that direction. And so if you can take this parametric equation for this ray and insert it for x, y, z in the equation for the sphere, then what will happen is you'll get a quadratic that the roots of that quadratic equation will be t, and if they're any real roots, then the ray hits the sphere. If there are no real roots, that meant there's no real solution to the combined equation. There's no x, y, z that'll make the combined equation true. Where what you're basically doing is you're saying, okay, I want a point that's both along this ray and on the surface of this sphere, right? That's what the math is doing. And there may not be a solution, in which case the results would be imaginary. You know, your square root, you'll be ending up taking the square root of a negative number. The ray could graze the sphere, right, at one point right along its surface. That's possible. In that case, you'll be taking the square root of 0 is what will happen in that case, which will give you 0. But that'll give you one solution. But normally, if it hits, normally what's going to happen is going to hit a front and a back, and you'll get a T, right? One of the T's will tell you the front intersection, and one of the T's will tell you the back intersection, and you'll take the smaller T because that'll be the nearer intersection. And so then remember, we're not just doing this for the initial ray that comes out of our eyeball. If we hit this point, we will then want to do a reflection and a refraction to see where that goes, right? So if we hit here, right, we might have we would have now a new ray, a reflected ray that goes out in some direction, and that reflected ray may hit an object. And so here, the intersection point of the previous ray is the starting point of the reflected ray, okay? So your starting point's not always going to be your eyeball. It's going to be, when you start, for the very first ray, it'll be your eyeball, or center of projection. But then after you've hit something, the next ray, the starting point will be that intersection point of the previous ray, and etc. Okay? But I didn't want you to get confused and think that everything we trace is always coming out of the eyeball. So what do? Well, we know that a sphere is all points that are equal distance array, that are radius distance away from the center point, and so you get this classical definition of all of the x, y, z points that are on the surface of a sphere here, right? That's just the equation for a sphere, and we also have the equations for our ray, right? If you've got 2 points, you can get the ijk, which is your vector, right? And any point x, y, z along the line will be that start point x, y, z plus the x component of the vector, the y component of the vector, the j component of the vector, and all of them times the scalar t, which tells you how far to move along. So basically, the x, y, x1, y1, z1 is saying, what's my starting point? The I, j, k is the x, y, z of the direction vector, and the t is how far along this direction, how far in this direction do I need to go? And basically, this will give you, for values of t, if you iterate through every possible value of t, that would give you every point along the ray, along the line. So we take that parametric equation for x, y, and z, and we plug it into our x, y, and z of our sphere, and that gives us this combined array slash sphere equation, and then we have to solve it. Well, the first thing you have to do is you have to multiply out all of these things that are squared and combine your terms, and you can get a quadratic a times t squared plus b times t plus c equals 0, and then these are the things that you collected together. Everything that was multiplied by t squared is in A. And you can look at it and say, you know, that's true, because if you look at like here, k squared is multiplied by t squared, right? So that's why k squared is here. And if we find j squared, we'll find the same thing. And if we find like j squared times t squared, so there's our j squared, right? And if we look here, we can find our I squared times t squared. So basically, the I squared plus j squared plus k squared are all of the things that are multiplied by t squared. So you pulled out the things that were multiplied by t squared, and then you pull out all the things that were multiplied by t, and then you collect everything that wasn't multiplied by either t squared or t, and that gives you the A, the B, and the C for this equation here. Let's see. So, okay. Stephanie has a question that it looks like Andrew answered it, but I'll go back and make sure that we're on the same page here. Stephanie, we need two things when we want to talk about array. We need to know where the ray starts, and we need to know the direction the ray is going in. The direction is just a vector that I'm calling ijk. If I'm given 2 points like the eyeball, the center of projection, and the point on the screen, I can do, you know, end minus start, x end minus x start, y end minus y start, z end minus z start to get the ijk. Okay, so I can compute the vector from any 2 points on the ray. So ijk is the direction I'm moving. ijk is the direction that I'm moving. T is how far in that direction I'm going to go. And x1, y1, z1 is where did I start. So if I've got a starting point, just think of it in the real world. I know where I'm going to start. I know what direction I'm going to walk in, and T tells me how far in that direction to walk. And that'll give me some point, x, y, z, along this path. X, Y, Z is just a point on the path. And which X, Y, Z you land at depends on how far, how big your T is. How far did you walk in this direction? Okay? So that's all of that. So once we've got our quadratic, we can then, you know, negative b plus minus the square root of b squared minus 4ac over 2a. That you learned back in middle school, I guess. Or I guess it's middle school. Again, if this discriminant is a negative, if b squared minus 4ac is less than 0, then because there's a square root of that, there's no real roots. That means that you're in this case. There is no t. Just think about it. Let's go back up to the picture. I love pictures. That's telling you that there is no t that you can use that will bring you to the surface of this sphere. When that discriminant is negative, there's no real solution that tells me what my t needs to be to reach the intersection of the sphere. If my t is 0, right, remember it's plus or minus the square root. Well, if that discriminant 0, the square root of 0 is 0, so you only get one solution. But if your discriminant is greater than 0 and is positive and greater than 0, then you're going to have a situation where, because it's plus or minus the square root, you'll have a minus and a plus. You'll have 2 points. And in that case, you'll take the smaller t. It'll tell you how far to walk down this direction from some starting point, how far to walk down this direction to hit the nearer spot on the sphere. Okay. All right. Everybody's with me now? Again, it's just high school math. But it's been a long time since you've been in high school. It's been an even longer time since I've been in high school. I give an example here. The math all works out, but I'm probably at some point going to replace this example, or at least build a, what I plan to do is I plan to build another version of this figure here, but with the actual numbers that are in that example. So I'll do that so that you'll have numbers to go along with the equations that I grind through. So that's my plan. There is I'll probably at some point I'll change the numbers in the example and build a little a graphic to go with it. So there won't just be sort of random numbers sticking out there. You'll have a picture to link them to. But I haven't gotten that far yet. But it works. All the math is correct. At least when I checked through it 3 times, it seemed correct. Okay, so that's how you get the intersection point with the sphere. You also have to be able to get the intersection point with a plane. So you do the same trick. Instead of starting with the sphere equation, you start with the plane equation. Cap AX plus cap BY plus cap CZ minus cap D equals 0 is a plane equation where D is cap A times little a plus cap B times little b plus cap C times little c. What is all of this crap, Michael? You confuse me with this. What it's saying is, here's a plane. This plane is defined by a surface normal. We usually call it, N, but we got so many friggin' letters here, we've got to find something for everybody. So we're calling our surface normal cap A, cap B, cap C. This is the X, the Y, and the Z of the surface normal. So that's the surface normal. But a surface normal, a vector, has to be anchored somewhere because it's just a direction and a magnitude. And if you make it a unit vector, it's just a direction. So you also need a point on the plane that defines that. So if you've got a point and a vector as a surface normal, then you've got a full definition of a plane. So little a, little b, little c is just an x, y, z for some point on the plane. Okay? So the cap A, cap B, cap C is the surface normal, and the little a, little b, little c is a point on it. And so this equation here, this is essentially the dot product. You can think of it as if you want to think of little a, little b, c as a vector, and of course cap A, cap B, cap C is a vector. This D is just a dot product. Basically, it's locking down where our plane is in space. And again, the A, the B, the C is the surface normal. So what's X, Y, Z? Well, when this equation equals 0, x, y, and z is a point on the surface of the plane, such as this point right here, x, y, z. So what we do is we take the equation for the plane, and then we go back to our equation for the x, y, z's along the vector. We still have a starting point. We still have a vector that gives us the direction. We'll still have a t that tells us how far to walk. And so we'll want to solve for t. How far do I need to walk in this direction before I hit the plane? That's what it's asking. And that is given by crouching through some math, and that gives us a t here. Notice there's no square root here, so you'll get just a single value, because a ray is not going to hit a plane in two different points. It's only going to hit it. It's either going to miss it or it's going to hit it at one spot. Now, this denominator can be 0. If the denominator is 0, all it means is, I think I have an image of it. Oh, no, I don't. If it's 0, all that means is that the ray shooting out of your eye is parallel to the plane and never intersects it, no matter how far you were to go. So that's the way that the equations tell us there's no t. There's no distance you can walk in the direction ijk, or in the direction ijk from starting point x1, y1, z1 that'll put you on the plane. The only way that will happen is if the ray is parallel to the surface of the plane. Make sense? Okay. So again, here's another example. I'm gonna rebuild it at some point here this week, hopefully, where it more closely matches this image here, instead of having a vector that points away from the user. And this is x, y, z. So I just used my old notes and grabbed the examples and converted them. But really, I want to make them match images. So again, there's nothing wrong with this example. It's a good example. It shows you how the math works. Everything's good here, but the plane is actually not in this orientation here. It's actually vertical with the normal pointing into positive z. If you think about this as the xy plane, and you think about this as positive z, the way we've done it. So I want to actually change the example so that it more closely matches the way we've been thinking about our projection system. But again, there's nothing wrong with the math. It's correct. The equations are right. Okay. And computing the reflection vector. So once we know the intersection points, we have to be able to compute a reflection and potentially a refraction. We've already given the equations for reflection. These came from when we were looking at the reflection of a lighting vector L, right? It's exactly the same equations, except some signs are going to change, because now our ray points towards the surface, where if you go back and you look, our lighting vectors always pointed towards the light source. So the incoming direction of this vector is backwards from the lighting vector. And because of that, it's going to cause some signs to swap. But that's the only thing that's going to happen. It's exactly the equations that we looked at before. R equals n plus t times 1 over 2 times the cosine of phi. And remember, you get the cosine of phi. Again, the cosine of phi was the dot product of the surface normal and the lighting vector. But now this is the opposite of the lighting vector, and that's why you have these little minuses here in front of your t's, because I had to flip it mathematically, because it's coming in rather than going out. Okay? Obviously, your n and t need to be normalized. I'm using t to, this capital T is not the little t we were just talking about how far to go. I'm using capital T here to say this is the traced ray. Okay, so That cap T is totally different from the little t's that we were talking about here, because the little t is the distance that you're going down the traced ray, cap T. So little t is how far I'm walking down ray cap T. Okay? Okay, blah, blah. So again, those would need to be unit vectors so that you can do the math. But remember, there are actually three cases. We normally think about this case where phi, the incident angle, is less than 90 degrees, but it could be 90-degree angle in case you graze by, and if you do that, the reflection vector is actually just t. Because t is already pointing in this direction, r is just a continuation, so r is simply t in this case. And then the last case that you could have is, do I ever need to worry about a reflection off of a surface where the incident angle is phi is greater than 90 degrees? And the only case that I could come up with when I thought about this long and hard was a case like this, where you have a reflection. I'm showing it as a reflection off a sphere. It could be a reflection off a plane. It doesn't matter, but it's a reflection, right? And that reflection hits the back side of a plane. And then you have a decision to make. The decision is are the back side of planes going to be visible? So far, they haven't been. When we've dealt with polygons have a front that if it's there, you render it, and the back it's invisible. Right, the back side of our polygons are invisible. So what about our planes? Are you going to just ignore intersections where phi is greater than 90? You could, which means that if you're below a plane, that plane will be invisible. Or maybe you're going to say, no, planes will be visible both if you hit the front side of it or you hit the back side of it. It's up to you if you are going to ignore it. So I'm showing here as two little dashed lines, R prime, reflection prime, and reflection double prime. So if you're just passing through it, then R prime is just equal to T. There's nothing to do because it didn't hit anything. I just zoomed right through it. But if you do want to do this, have it bounce off the back side, then it's the same thing that we did before. If you go back and look at the lighting equations, this is just the case where phi is greater than 90 degrees. Again, you do have to yeah. So phi is greater than 90 degrees here, and you've got a bounce. Okay. And you just, so R double prime, again, it's the same thing that we did with our lighting equation. It's just that some of the signs get flipped. And so then I worked through a complete example of a computation of the reflection vector for a traced ray where the angle is less than 90 degrees. And I grind through the math, and that all matches with what this here. And you notice I did put what the actual surface normal was. I did put what the actual angle was. I did put what the actual cap T was and what the actual reflection vector. I gave the numbers here, and those are the numbers that I computed here, right? So your reflection vector, the math for running through it matches the image. That's why I want to go back, and for my intersections, I want to do the same thing. I want to give you an image and run through math that matches the image. The last thing is the refraction vector. And here again, these are real numbers. If you've got the transmitted ray, the reflected ray, a 45-degree angle, a surface normal of 0, 1, 0, surface normal of 0, minus 1, 0, And if the density of air is 1 and the density of the sphere is 2, I don't know, it's only twice, so it's more like a soap bubble or something. It's only twice as dense as the air. You'll get a refracted ray like that. And these are the actual numbers. How do you know they're the numbers, Mike? Well, here are the equations. I'm just presenting them to you. I'm not going to try to derive them. It's not that important because you're not going to use transmitted rays in your assignment unless you want to go and really impress me. That's good. You should, Eric. Go out and do the transmitted ray. All the math is here if you want to do that as kind of a personal stretch goal. That's why I'm giving it to you, but I'm not going to take a lot of time on it because most of you aren't going to implement it. But anyway, here are the calculations, and you see that they do work out. And oddly enough, the magnitude, I didn't have to normalize it because the magnitude of the transmitted ray ends up being a unit vector. So that's where these numbers come from, are all those calculations. Okay, so any questions about that? I know we quickly went through this last time, but I wanted to take more time and go through it more slowly. If the first thing it hits is the back side, wouldn't that mean it's inside another shape due to clipping? Well, we're not doing any clipping. Again, the situation I assume you're talking about this problem, Andrew, or are you talking about a different problem?
Yes, that one.
Right. So there's a plane that think about. We're going to put some spheres over a checkerboard, right? What happens if we were to raise that checkerboard so that it was above the spheres? Would it vanish when it went above our line of eyesight, or would you be able to see it from below? That's the question. If it vanishes, you've got this here. There's no intersection, essentially. If that checkerboard would still be visible even if it were above you, right? Even if you moved it above you. So if the surface normal is pointing like this, but you're down here. If that's the case, you'll need to worry about this greater than 90-degree incident angle. But it's basically, what I'm saying is, it's your decision as to how you're treating that object, as to whether or not you're gonna consider this as an actual reflected case. Okay. Okay, so what's a big outstanding question that we haven't attacked yet? Well, I keep talking about this checkerboard, and you guys, we've dealt with planes. When you look at Unreal, it's easy for you to slap a texture on a plane, right? You just pick a texture and go slap, put it there, right? We haven't really talked about mapping a 2D image onto a plane. But you should think that it's probably not that bad. Instead of that, though, we are going to have a checkerboard, and we will algorithmically generate the pattern onto the plane, is what we're doing here. So how do I algorithmically generate a checkerboard pattern? Well, first of all, this checkerboard is going to be in the XZ plane. It's going to be in the XZ plane because we're looking at it. Hold on. What page is this? So I can get back to it quickly. 121. This plane, we're above this plane looking down at it slightly. So this is, this horizon here is pretty much y equals 0. Okay, so this plane is actually located at some negative y, but it's a constant negative y, which means the plane is drawn in the x, z, left to right into the distance. Left to right's x, z is into the distance, so this is drawn in the xz plane. So what did I say, 121? Oh my God. We're close. So, I think I got myself into that. Okay. So this is the XZ plane, and we're looking right at the middle of the checkerboard. So again, think about this. I'm looking down at the checkerboard. I'm looking from, in your mind, imagine our XYZ. I'm looking from plus Y down at the XZ plane. This is the orientation here, okay? So the origin is here, and we know positive X goes to our right and negative X goes to our left. As we go forward in Z, those are positive because we're in our left-hand system, right? So the negative Z's would be down here, but we're not drawing them because remember we're out here. Our eyeball is out here in space somewhere, again, looking down at this whole thing, right? We're in negative Z. So positive X, positive Z. No, Andrew. What I'm doing here is we're in your code. We are not going to move where we're at. I'm trying to show you the board from a different viewpoint so that you will be able to understand how to compute the checkerboard pattern. So this image that I've drawn here, how could we get this image? We get this image because we are in positive Y, looking down towards the origin. We're not going to project this thing or anything like that. You don't want the Ralston Purina logo to be rendered, right? But for this particular image here, I wanted to show you the checkerboard pattern from above. Okay, but we're not going to change the way that we're going to be doing any projections or anything like that. Okay, so again, X goes positive to your right, it goes negative to your left, Z goes positive looking forward, negative going back towards wherever your center of projection would be. So we can see that it goes red, white, and if we go here, it goes white, red. So, and then as we go forward, it's red, white, or if we start on white, red, we can see it's flipping, right? And so I can also see that each of these squares, the way I've got it defined here, is a 100 by 100. I actually think it looks better if you make the squares 200 by 200 in your drawing, but I wanted to put a lot of squares here, so I used 100 by 100 for the example here. But when I actually built it and projected it, it looked better with 200 by 200 squares. Okay. Now, you can think of this as going a pattern, a red-white pattern or a white-red pattern is repeated every 200 units. I'm at 0, I've got a red square and a white square. I'm at 200, I've got a red square and a white square. I'm at 400, I've got a red square and a white square. Or if I start white-red, I start at white, I go to red. If I go 200 left, right, I'm now ready to have a white square followed by a red square. If I got 200 more left, there would be a white square followed by a red square. So this pattern of red, white, if I'm going right, or white, red, if I'm going left, repeats every 200 units. It also, in X, it also repeats every 200 units in Z. White, red, okay, but I move forward 200, and then it's white, red, and then I move forward 200 units more, and it's white, red, or if I'd started at red, right, it's red, white. At 200, it's red, white. At 400, it's red, white. At 600, it's red, white. At 800, it's red, white. So it just repeats the pattern every 200 steps in X and every 200 steps in Y. Okay. And that's really all you need, because here's the pseudocode for generating the checkerboard. If X is positive, then color flag equals 1. Color flag 1 means red, color flag 0 means white. So if I've got a positive number, if my X is positive, I'm going to go over in this direction here. So I'm starting with a red square. If X is negative, I'm going in this direction and I start on a white square. So that's what this says. If your X is positive, then you're somewhere over in here and you start on a red square. If your X is negative, you're going in this direction, so you're going to start on a white square. So if X, absolute value, mod 200, it doesn't matter if I'm moving left or right, that's why it's absolute value of X, mod 200. So every 200, we restart our cycle. And if restarting our cycle, I am greater than 100, then I flip my color flag. Okay, you're probably going, what are you talking about here, Michael? Let's just say I've got a number like 50, okay? 50 is greater than 0, so the color flag is red. I'll be somewhere over in here, okay? If the absolute value of 50, which is 50, mod 200, well, that's just 50, right? If that's greater than 100, then flip the color flag. Well, it's not greater than 100, so I stay red. But let's say instead of being at 50, I was at 150. So 150 is positive, all right, it's greater than 0, so I start with a red color flag. I start with a color flag of 1. If the absolute value of 150, which is 150, mod 200, that's still 150. If 150 is greater than 100, it is flip the color flag. So it was red, now it flips to white, because at 150, I should be on a white square. Does that make sense? What if it was the other direction? Let's say that I'm here and I'm going to move to minus 250. Well, minus 250 is not greater than or equal to 0, so the color flag starts at 0. I'm going to start on a white square because I'm moving leftwards. Okay, minus 250, absolute value is 250, mod 200 gives me a 50. Is 50 greater than 100? No, so I don't flip the color flag. I'm here, I started at white, I'm at 250, and I stay white. If I had been at 350, right, I would have flipped again, because 350 mod 200 is 150, and 150 is greater than 100, so that flips the flag from white to red in this case. See how that works? Okay, now we got the first row down. What about all the other rows? Well, you just do exactly the same trick. Now that we're at the starting color of our row, I look at Z and do the same thing, because it's going to flip, it's going to restart every 200, right? And I need to see, okay, am I greater than 100, or am I not greater than 100? If I'm greater than 100, I've landed in a position where I need to flip again. So that's what that is. And then finally, your color flag is either red or white. Okay, and so these little 4 lines of code would return the color red and the color white, depending on what square you're on. And if you want to look at it, I actually run through some more numbers where I look at 275, 450, and you can see I go over 275, that means it's on the red, and then I go up 450. So if you're having a little trouble with it, I worked out 2 examples so you can see exactly what that code is doing. Okay, that's how you get the checkerboard. Okay. So at this point, you really have everything you need to write the program. You know how to ray trace. We've talked about that. It's a recursive procedure, right? That's going forward. You need to be able to tell whether a ray intersects a sphere or a plane, and you need to be able to compute the reflection or the refraction from the intersection point. We're not really going to use the refraction unless you want to really go out and impress me. We'll just use the reflections, but I gave you both. And you need to figure out, how do I make this thing look like a checkerboard? And we just went over that. What are some ways of improving things that we're not going to do in our programming assignment? Well, one of them is multiple rays per pixel. You might be thinking to yourself, Mike, come on, dude. We just talked about the fact that if I do reflection and refraction and only go 4 levels deep, I could be talking about 15 intersections per pixel per frame. This is crazy talk. Now you're talking about shooting multiple rays through every pixel. I already can't afford to do full ray tracing, and now you're saying, oh, we'll just shoot multiple rays through the pixels. Why would you want to shoot multiple rays through the pixels? Well, ray traced images look too perfect. We go through all of this work to figure out the shadows and reflections and stuff like that, but we end up with things that look too perfect. I hate going back a little bit. You're never, could that exist in the real world? Well, the spheres are floating, but you could put them directly on the plane. But are you ever going to get something? You might be able to get something close to that, right? But these shadows, they don't have any fuzziness to them at all. They're perfect, right? And these reflections, they get more tinier and dimmer, but they're perfect. There's no blurriness in these spheres, right? And in the real world, even your shiniest of silverware or shiniest of crystal balls or Christmas ornaments, if you look at them real close, you'll see they got little tiny scratches on them, right? We take such good care of our phones, but then if you look at it, you go, oh, you can see all the little scratches that are on your screen, right? Well, when rays hit a plane, if there's scratches on it, there's imperfections, and even if it's brand new out of the box, that glass is not perfectly flat. I can guarantee you that. If you get it under a microscope, you'll see the little pits and grooves and all of that. And that's before we use it in the real world. So in the real world, rays are not going to reflect and refract in the perfect way that we are mathematically computing, because a ray is never going to hit a perfect sphere. A ray is never going to hit a perfectly flat plane. Those don't exist in the real world. So that's why these things look a little too perfect. So one of the things that we can do is we can say, well, if I put multiple rays per pixel, there are kind of two ways of doing it. There is the smart way. You might say, well, there's no way I'm ever going to afford multiple rays per pixel. 4 rays per pixel, that's crazy. But think about it like this. Instead of shining the rays through the center of the pixel, think of each pixel as a little rectangle, and I shine the rays through the corners of those rectangles. If I do that, I'm really only going to have, instead of n times m rays, right? I'll have n times n plus m plus 1. Do the math and you count it out. You're getting most of the rays, like this ray right here, this puppy. It's shared by 4 pixels. Most of the rays are shared by 4 pixels. It's only like the corner and the top rays here that are only used by 1 pixel. So you end up using very few additional rays. And what you do is, to figure out the color of this pixel, I average the color returned by the 4 corner rays. And that'll give me a color for this pixel. And the color for this pixel will be averaged from its 4 corner rays, et cetera, et cetera. So by shooting the rays through the corners, you can 4 times oversample without really doing 4 times the amount of work. So that's a little trick that gives you, in fact, in a 3,800 by 40 by 2,160 image, if we used this to do 4K oversampling, we will only look at an additional 0.07% additional rays. So for a big image, it's a very tiny number of additional rays that you're casting to be able to do 4 per pixel, because most of the rays will be used by multiple pixels. Now, you could do a more expensive version where you actually shoot 4 rays through the center of that pixel. Now, if you did that, you didn't change anything else, it wouldn't change the look of the image at all, because each of those rays are following the same path, and so when they do an intersection, they will do exactly the same calculations, and they will have exactly the same reflection and refraction vectors, which will end up hitting exactly the same points on the other objects, which will reflect and refract in exactly the same way. So shooting multiple rays through the center of the pixel isn't going to change the image unless you add a little bit of noise. And that's a technique that's often used, which is when I compute my reflection vector or my refraction vector, I then go and by a teeny tiny random amount, I jiggle the X, the Y, and the Z values. So that way, every time a ray passes through and hits a surface and reflects and refracts, those reflections and refractions will go out in slightly different directions. When you sum it all back up, you end up with blurriness. And you can control the blurriness by how much you control the amount of random jiggle that you're going to do. Seems sad, though, that you put all this work into making things look perfect, and then you're going to spend extra work to degrade the image to make it less perfect. The irony of that is not lost on me. But the real world is not perfect, and so it's going to cost you money to capture real world imperfections. So, anyway. Also, yeah, this is why we can't have nice things comment. Remember for a 4K image, if we're going to trace rays, we're looking at 8,294,400 rays that go through pixels. And each of those, of course, are going to generate their reflections and their refractions. So if you're doing that 4 levels deep, it's that number times 15. And that's why you don't see a lot of complete ray traced images in real-time graphics for video games. One other little thing we can do, another little technique, this one improves realism by letting you go deeper where you need to, like in highly reflective areas, but not go as deep on areas that are less reflective. And that's called adaptive depth control. And basically what you do is you set a cutoff and you say, okay, look, I'm not going to go any deeper when the intersection of this ray won't give me any more than, say, 10% of the overall color of this pixel. It's just not worth the cycles to do that. I can live with the fact that this pixel might be 10% off in its color rather than do the calculation, the intersection, and all of the, because remember, you have to do Phong illumination models at each of these intersection points. That gives you the local color. Okay, so that's just adaptive depth control. Shadow feelers, I need a pretty picture for this, but the words are right. Basically, every time you hit a point on the surface, you send a ray back into the direction of your lighting source to see if it hits an object. And if it does, then you turn off the diffuse point and specular components of the local illumination model. So again, every time we do an intersection, we ultimately want to get the color of this pixel. The first intersection is going to have some local color. That local color will be computed from the Phong illumination model. You'll have your ambient, you'll have your constant of diffuse reflectivity, you'll have all of those calculations you will do here to get the local color. And that local color will be some percentage of the color here, maybe 25%. And then the reflected and the refracted ray will also contribute some amount of color. Maybe in this case, we're not doing refractions, but maybe the reflection, maybe this is highly reflected. So 25%, say, of the local color comes from the Phong illumination model, and 75% comes from whatever we get back from the recursion going down this ray. And you do that at every friggin' point that you hit. So it's not just an intersection calculation and a reflection and a refraction calculation, it's also a Phong illumination calculation at each of those points. Okay? Eric, we're talking about a very tiny change there. I would say, depending on your scale of things, probably the smallest one you have there. But you know, you can experiment with it at different numbers and look at the blurriness of it and see what works. That's what we call empirically determining a value. You just fiddle with it until you get something that looks good. Now, you do have to realize that objects can be partially translucent. And in that case, you might not want to block all of the light coming from a light source. You might want to block a part of it. So let's say you had an object that's 25% translucent. So it's like a Christmas ornament that's made of glass, but it's got a dark color to it. So you can see through it. If you hold it up to the light, you can see, oh, this is a red Christmas ornament, right? But it does transmit some light, but most of the light's reflected. So in that case, if one of those objects, a partially translucent or partially transparent object, is between you and the light source, instead of completely eliminating the point diffuse and the specular component of the Phong illumination model, you would multiply them times the percentage of transparency to decrease the effect of that light rather than flipping it completely off. Okay. Questions about any of this before we look at the example that I have here? By the way, I've been talking about changes I'm going to probably make to these notes. I'm probably going to get rid of this example. So I would encourage everybody to save off this version of the notes, because by the end of the quarter, or a few days from now, when you're working on your programming assignment, you may have found that the notes have changed and no longer include the old program. Instead, I think what I'm going to do is, when I finish my program, I've started on it. When I finish it, I may go back and put sections of it in the text and omit sections. So next year, they'll have a partial, instead of having a complete program in a different language, they'll probably have a partial Python program that'll have the framework, but all of the calculations for doing the intersections and stuff like that will be left on the floor for them to fill in. At least that's what I'm thinking. I might change my mind, but that's what I'm thinking about. So I encourage you to save off this version of the notes. So what does this thing do? What does it not do? It does not implement a full font illumination model. It just does the local color is just treated as an ambient color that I set. My checkerboard in this code is non-reflective. Yours must be reflective. I don't implement shadow field arrays. You should do that to get some extra points. And this code has a color table reduction mechanism in it that's a holdover from the time before you were born, because computers, even high-end workstations that cost $10,000-$20,000 could show color, but they couldn't put, they were limited in how many colors they could put on the screen at one time. And so the machine I built this on was limited to 256 different colors out of a palette of 24 million that it could show, and so I had to do some fancy crap to be able to do it. The other thing is, this is god-awful code, which is probably why I'm not going to include it in the end. It is not at all object-oriented. But what does it do? It does show you the recursive nature of ray tracing. It does show you how to do the intersection calculations, the calculations that I gave you the math for. It shows those converted to computer code, and it shows the calculation of reflection vectors in computer code. So we start off, we've got a driver program that's going to basically have a center of projection, and then it's going to go through X and Y. You'll have a doubly nested loop to get you through the every pixel on the screen, because you've got to scan through it and get a vector for each one of those. Here's the vector, IJK. Remember IJK from our math? Well, ray I, ray J, ray K. There they are. End minus start. Boom. That gives you the vector there. I didn't normalize it, probably should have. And then I send that into a trace ray with some depth that I'm going to go. I'm going to fall out when I reach a depth of 0, I think. And then this is how you put a pixel in that system. So here's our ray tracer, trace ray. It's got a bunch of crap. It's got a bunch of more crap. When you reach 0, you're at your max depth, you turn black. Otherwise, you check for an intersection of the ray with each of the objects. We're going to want to find the shortest object, so I set t at some ridiculously large number. We're going to look for the intersection with the smallest t. I used a kludge that had an object code, like each of my spheres had an object number and my plane had an object number. So I set that to -1, meaning I haven't hit an object. Do a checkerboard intersection. And a little flag that said, yeah, I hit the checkerboard. Do the sphere 1 intersection. Do the sphere 2 intersection. These spheres should really be objects. They're not. They should be. I would almost say, if you want full credit on that 10 points that I've always been giving you guys for free, you better at least try to implement things in an object-oriented manner, because you just need to do that. I'll take off a few points if you just transliterate this code. And then once we know the object, I went here and I had to calculate the intensity. And if you don't hit anything, you set the color to the background color, the skybox color. So what does the checkerboard intersection look like? Oh, look, you got a plane normal, A, B, C. You got a point on the plane. Well, we had called this in the math cap A, cap B, cap C, and we had called this X1, Y1, Z1. We had called that little a, little b, little c, but it's the same things. You compute a denominator. This is the checkerboard intersection. So if that denominator is 0, I check to see if it's very close to 0. Because when you get close to 0, your intersection is going to be almost at infinity. So I didn't want that. So if I'm close to 0, I say it didn't hit it. I'll treat it as parallel. And then you go through and you say, okay, well, let me compute the cap D. I'm calling it little d here, but the cap D for the plane. And then you've got your numerator over your denominator. That gives you your T. I'm calling it T object. And then look at this. This is exactly the start point plus the IJK of the ray. I'm calling it XYZ here, but it's the IJK, right? And the T is how far down you go. And you do have to do a check here to say, if, remember we have these rays and we have these planes, right? What if you've got a ray that's going like this, you say, oh, it doesn't hit the plane. Well, actually, it does hit the plane down here, right? If this is my eyeball and I'm looking in this direction and my plane is over here, I do get an intersection, but it's behind the back of my head. So if my if my T is less than 0, which means it hit behind me, or it hits, maybe it hit in front of me, but it hit in negative Z, we don't generate negative Z, that's the space between us and the screen, or if it's way too far off in the distance, just treat it like it didn't hit it. There's no visible intersection, so return 0. Okay, I didn't hit it. Otherwise, if you have to check to see if this is the closest T, you'll have to do that somehow. If it passes all of those things, the XYZ is the intersection point, and you return the 1, meaning, yeah, I hit it. And then you got the thing to do the intensity. Doesn't this look familiar? If X is greater than or equal to 0, color flag is 1, else color flag is 0. If the absolute value of blah, 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 blah. See, that looks very similar, doesn't it? If the color flag, make it red. And again, you should be doing a font illumination calculation here, but I'm just using ambient. All right. Red or white. And I'm using 255 to 0. You should probably be using 0 to 1. Similar thing for the spheres. You've got a center point, you've got a radius, you calculate the A, the B, the C, you calculate your discriminant. If that discriminant is less than 0, then there was no real roots, there's no intersection. If it's greater than 0, there are 2 intersections, right? TS1 and TS2, you take the smaller one, and then if there's another object that's closer, you say, oops, I'm not going to count this one. But otherwise, again, if the T is less than 0, it intersected behind you. But otherwise, you calculate the intersection point. You then have to do an intensity calculation. Doesn't that look familiar? This is the getting the reflection vector here, because to get the intensity, right, I have to call my trace ray recursively on the reflected ray, and then once it returns, I can add in the effect of local color to the returned color that came from the trace ray. And I do that for 2 different spheres there. And that's really about it. Where is my code? Oh, I was going to show you. I was going to show you my my program running, but it looks like I show all windows. Okay, here we go. I notice we're out of time, so if some of you need to drop off, you can go ahead and drop off now. But here is, let me show you what it looks like actually. Here is my Oh, crap. One sec. Ah, here it is. I just started on the programming assignment. So, and of course, it doesn't want to share the contents of that window. Let's see if I can run it. Again, if you need to go, because I know I've gone over time here. Let's see. Come on, Mr. Bond. I've got too many windows on the screen. Oh well. Suffice to say that it's got the checkerboard, but that's the only thing I've implemented so far is the checkerboard. But I did want to show. Let's see. There it is. Am I sharing that?
No.
No. How about now?
There it is.
Okay. So you got the sky, you got the checkerboard, you can see that the pattern all works right. If we look at the code, if we look at the code, you can see that I have a class for sphere. And when you create that sphere, you need a center point and a radius, a local color, and then the weight for the local reflected and refracted. And we set up these variables, right, from what you passed in. I haven't yet created any intersection calculations for that. I've done the same sort of thing with checkerboard, but I've gotten further. You define the checkerboard. It's got a surface normal and anchor point, a local weight and a reflected weight. We're not going to do refractions on the checkerboard. And so you save off the surface normal, the anchor point, the local weight, blah, 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 and a local color. And we've got a method that does intersection. This might look kind of familiar, right? I've Pythoned it more, right? And you can see I changed the variable names so they match the math that I've done. So cap D, right, is basically the surface normal times the anchor point. That gives us the cap D. And then the numerator for T is, if you look at the math, you can start at D and subtract off each of these guys, and that'll give you the T numerator. So T is the numerator divided by the denominator. And then here are the little intersection points, your start point plus your ray times your T, right? And then here's seeing whether or not I have a negative. Remember, this is Z, so did it hit in negative Z? Did it hit too far in the future? Did it hit behind my head? Otherwise, we're going to, if it passes all of those, we're going to set the local color. And here is my calculation for color. And since Python doesn't have binary operators, I simulated that by always adding 1 and doing modulo 2 math. So it'll count 0, 1. When it gets to 2, it'll go back to 0. So 0, 1. So every time you add 1, that flips the flag. I thought that was a cute little way of implementing binary without having the ability to actually have bits that I can flip. When I define things, now because I'm actually using objects, I can just define a red sphere, right? I can define a green sphere, I can define a blue sphere with a center point, a radius, a color, and my weights. I can define my checkerboard. I've only got one of them, so you could argue whether or not you needed to do an object here, but I did. And then the render proc basically goes through each pixel on the screen. You got that, and then it calls trace ray from the center of projection ray. And right now I'm not tracing anything. I'm just seeing, well, I'm tracing one thing. I'm seeing if I intersect the board, and if I do, I return the board's local color. Otherwise, I return the sky color. And that's about it. We got normalized. I changed up my code for computing hex color codes a little bit. One of them just takes in a vector of red, green, and blue. So you can just send it as a list of red, green, blue. Or if you want to, you can keep red, green, and blue separate like we did before. But anyway, this computes that. Because some of you ran into problems with color hex code, I added a little bit of error checking to make sure that when you're computing an intensity that it's not greater than 100% or less than 0, because that would screw up the calculation. So I explicitly put those checks in there and put those limits to keep it from erroring, because some of you guys ran into problems. And that's an old comment. Look at that, rendered the 20 spheres on it. Old comment. See, I'm just getting started, but you can see that the structure is way different than the code that I gave you guys. This is far more object-oriented and just more reasonable than the code that's there. So I may change the I have to decide what I'm going to do with the program, because I don't want to give too much, but I don't want to give too little, and that's always hard for me to decide how much is too much and how much is too little. But you can see what I'm doing there. Any questions? Well, there are some questions here. Do I have a screen cap of fuzzy image? No, I don't. Do we need to be able to move the spheres around, or should it just produce a static image? Static image, Brian, I may ask you as part of your walkthrough to change where an object's at. If you want to build an animation, you're free to do that. You might be able to get a frame every few seconds out of it. Or, you could build it so it computed a frame and then paused and waited for screen input, and then do a screen capture and do a series of screen captures to make a movie. And in fact, that's how, when you're talking about graphics that are actually used in movie production and stuff like that, they don't render those things in real time. They render it, they save it off, they render the next one, they save it off, and then they just play it at, normal speed. So there are a lot of ways that you could do that. Is this supposed to be a new program from assignment 1 through 4 or added on to those? This is a new program. As you can see from my code, I pulled some things like a color hex code. I'm pulling normalization routines. I'm pulling, dot product. So there's a lot of methods that you'll go, oh yeah. So basically, when I was writing this last night, I had my other programs opened in other windows, because I need normal. I can grab that from this one and pull it over. And you can see how one of the comments came from the 20 spheres example, right? So yeah, you're gonna reuse a lot of things, but there's gonna be a lot of new stuff too. Other questions?
I have a question that's not related to the assignment, but to the presentations on like Wednesday and Friday. Do you want those to be in the same style as we did for the midterm, where we had like a PowerPoint and the game, or do you want it to be like more focused on the game, like playing through it and what it looks like inside Dungeon?
Both. Remember, these are longer presentations, right? This is not just a stand up. You're going to have, I think each team has at least 20 minutes, right? So you should be able to, yes, we want to see what you did. So maybe the bulk of the presentation will be showing off the game and talking about it, but there should be a PowerPoint that says what you did and stuff like that. For me, now again, I'm not grading it, you guys are grading it, but for me, the most important thing that I like to hear, that I always ask, is what did you do and what did you borrow or take off the web? And there's nothing wrong with taking tons of stuff, but to kind of judge how much work went into it, you need to tell people, you see this chair, it might not look like much, but I built that chair from scratch, right? I didn't just pull it off the internet. And also, if you've got something that's really spectacular looking, make sure people know, that came from this. Sometimes people, I remember one of the groups, I don't remember which one it was, but they had this, the skate pod thing that crashed. I liked the one that you guys did yourself better than the one you got off the internet. Yeah, yours wasn't quite as detailed, but I knew you put time in and built it. All right. That meant more to me than I grabbed this object. So, grab objects, make your world look as great as possible, but have things that you can point to, say, we did this, and here's where we spent most of our time doing this, so that your peers who are judging it won't just think, oh, he just took that effect. If you programmed it, you need to tell people. Does that make sense? Okay. Alrighty, guys. I will see you all, I suppose, on Wednesday. Have a good day. Talk to you later.